watchers of the heavens. Early astronomy and the night sky. Darkness falls across the land. As the last light fades from the western horizon, the sky transforms. One by one, points of light begin to appear, faint at first, then growing brighter as the darkness deepens. Within an hour, thousands of stars emerge, scattered across the vault of heaven in patterns that have remained unchanged for millennia. This is the night sky as our ancestors saw it. No city lights washing out the fainter stars, no satellites tracking across the darkness, no aircraft blinking their way from horizon to horizon. Just the pure, undiluted spectacle of the cosmos, spread out in all its magnificent complexity. For most of human history, this sight greeted our ancestors every single night. And they didn't just look at it, they studied it, with an intensity and dedication that would rival any modern astronomer. This is the story of humanity's first systematic science, the story of how early astronomers turned simple observation into mathematical prediction, how they built monuments aligned to celestial events with astonishing precision, and how they came to understand that the lights in the sky weren't random, weren't chaotic, but followed rules that could be discovered, recorded, and used. It's a story that spans continents and millennia, from the plains of ancient Mesopotamia to the jungles of Central America, from the stone circles of northern Europe to the desert observatories of the Middle East. And it all began with the simplest of questions. What are those lights in the sky? And why do they move the way they do? The eternal dance. Every night, the same drama plays out across the sky. As darkness falls, stars appear in the east. Through the night, they arc across the heavens, reaching their highest point when they cross an imaginary line running from north to south, what astronomers call the meridian. Then they descend toward the west, eventually disappearing below the horizon. To a casual observer, this might seem random, chaotic, but watch carefully, night after night, and patterns emerge. The stars don't move randomly. They move together, as if they're all fixed to an invisible sphere that rotates around the Earth. The pattern they form, what we call constellations, never changes. The stars that form the shape of a great hunter in autumn are always in the same relative positions. The bright stars that trace out a great square in the summer sky always maintain their configuration. Early astronomers noticed this. More than that, they noticed that if you watched from the same location at the same time each night, the entire pattern shifted gradually. Stars that rose just after sunset in one month would be high overhead by the same time the next month. The sky itself seemed to rotate through the seasons, completing a full cycle in roughly 365 days. But there was something else, something that didn't follow the pattern. Among the thousands of fixed stars were a handful of bright objects that wandered. Night after night, these objects moved against the background of fixed stars, tracing complex paths across the sky. Sometimes they moved in one direction, sometimes they stopped, sometimes they even seemed to move backward before resuming their forward motion. The Greeks called these wandering stars planets, from their word, planets, meaning wanderer. There were 5 visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. Add to these the Sun and Moon, which also moved against the background of stars, and you had 7 celestial objects that refused to stay still. Understanding the movements of these wanderers would become one of the great obsessions of ancient astronomy. The first observatories. In the flat plains of ancient Mesopotamia, between the Tigris and Euphrates rivers, a civilization emerged that would transform humanity's relationship with the night sky. The Babylonians were meticulous record keepers. On clay tablets using wedge-shaped marks pressed into the soft clay before it was baked hard, they recorded everything: business transactions, legal disputes, royal decrees, and, crucially, astronomical observations. Thousands of these tablets survive, stored in museums around the world, and what they reveal is astonishing. The Babylonians weren't just watching the sky casually. They were conducting systematic, long-term observations, recording the positions of celestial objects night after night, year after year, generation after generation. Some tablets record observations spanning centuries, with each generation of astronomers adding to the records kept by their predecessors. Why? What drove this obsessive documentation? Partly, it was practical. The Babylonians used the moon to mark time. Each month began with the first sighting of the crescent moon after the new moon. Their calendar was lunar, based on the cycles of the moon rather than the sun. But lunar months don't align neatly with solar years. 12 lunar months fall short of a solar year by about 11 days. Over time, the calendar would drift out of sync with the seasons unless corrections were made. By keeping careful records, Babylonian astronomers figured out patterns. They discovered the Saros cycle, a period of approximately 18 years and 11 days after which the pattern of eclipses repeats. If you knew when an eclipse occurred, you could predict with reasonable accuracy when the next one would happen. But there was another motivation too, one that seems strange to modern scientific thinking: astrology. The Babylonians believed that events in the heavens reflected events on Earth, that the movements of the planets and the occurrence of eclipses could portend the rise and fall of kings, the outcomes of battles, the success or failure of harvests. If you could predict celestial events, you could predict, or at least prepare for, terrestrial ones. To our modern minds, this might seem like superstition, but consider what it led to: the most systematic, long-term program of astronomical observation in the ancient world. The Babylonians developed mathematical techniques to predict planetary positions. They created tables of celestial motions. They discovered numerical patterns in the movements of the moon and planets. In pursuing what we would call pseudoscience, they developed real science. Circles of stone. While the Babylonians were making their meticulous records on clay tablets, other cultures were encoding their astronomical knowledge in a very different medium: stone. On the Salisbury Plain in southern England stands one of the most famous prehistoric monuments in the world: Stonehenge. Massive stones, some weighing more than 25 tons, arranged in a complex pattern of circles and horseshoe shapes. The largest stones, called sarsens, were dragged from quarries more than 20 miles away. The smaller blue stones came from even farther, from the Preseli Hills in Wales, over 150 miles distant. The effort required to build Stonehenge was enormous. Hundreds of people working over many generations, moving stones that weighed as much as a dozen elephants, shaping them with stone tools, raising them upright, capping them with horizontal lintels. Why? What purpose could justify such an extraordinary expenditure of effort? For centuries, the answer remained mysterious. Theories ranged from the plausible to the absurd. It was a temple, a healing center, a place of ritual sacrifice, a landing site for alien spacecraft. But careful study of the monument's alignment has revealed something profound. Stonehenge is aligned to celestial events with remarkable precision. Stand in the centre of the stone circle on the morning of the summer solstice, the longest day of the year, and you'll see the sun rise directly over a massive outlying stone called the heel stone. The main axis of the monument points to this sunrise with an accuracy that cannot be coincidental. Similarly, the monument's alignment marks the sunset on the winter solstice, the shortest day of the year. Stonehenge is, among other things, an astronomical observatory built in stone. It marks the turning points of the solar year, the moments when the sun reaches its northernmost and southernmost points in the sky before reversing direction. But Stonehenge is far from unique. Across Europe, hundreds of stone circles, standing stones, and megalithic monuments show astronomical alignments. The Great Passage Tomb at Newgrange in Ireland, built around 3200 BCE, older than Stonehenge, older than the Egyptian pyramids, has a roof box specially designed to allow light to penetrate deep into the chamber only on the mornings around the winter solstice. These monuments represent an astronomical knowledge that was encoded not in writing. These cultures had no writing, but in stone and earth, in monuments designed to last for millennia. The knowledge they represent is profound. To build these monuments, ancient astronomers had to observe the sky carefully enough to determine the exact points on the horizon where the sun rose and set on the solstices. They had to understand that these points changed throughout the year, reaching their extremes on the solstices before reversing direction. They had to think in long timescales, planning monuments that would remain aligned for generations. And they succeeded. 4,500 years after Stonehenge was built, its alignments still work. Every summer solstice, the sun still rises over the heel stone when viewed from the centre of the circle. The moon's mysteries. Of all the objects in the night sky, none played a more important role in early astronomy than the moon. The moon is the night sky's most dramatic performer. Unlike the fixed stars, which remain constant in their patterns, or the planets, whose movements are slow and complex, the moon transforms itself night by night in an obvious, unmistakable cycle. A thin crescent appears in the western sky just after sunset. Each night it grows fatter, rising later, staying in the sky longer. After about a week, it reaches half full, what astronomers call first quarter. The waxing continues until, roughly 2 weeks after it first appeared, the moon rises as the sun sets, a perfect circle of light, full moon. Then the process reverses. The moon wanes, shrinking night by night, rising later and later. Last quarter, then a thinning crescent in the pre-dawn sky, and finally, the moon disappears entirely for a night or two, new moon, before the cycle begins again. This cycle takes approximately 29.5 days from new moon to new moon, a period called a synodic month. It's so obvious, so regular, that almost every culture in history used it as a basic unit of time. But there's a problem with lunar timekeeping. Lunar months don't align neatly with solar years. 12 lunar months total about 354 days, 11 days short of a solar year. If you use a purely lunar calendar, the months slowly drift through the seasons. A month that falls in summer 1 year will fall in spring a few years later, then winter, then autumn, cycling through all the seasons over a period of about 33 years. This works fine if you live in a place where the seasons don't vary much, but it's problematic for agricultural societies that need to know when to plant and harvest crops. You need to track both the moon, for short-term timekeeping, and the sun, for marking the seasons. Ancient astronomers solved this problem in various ways. Some cultures used a purely solar calendar, dividing the year into 12 months of roughly equal length, divorced from the moon's actual cycle. Others used a lunar calendar, but added extra months periodically to keep it synchronized with the seasons. But understanding the relationship between lunar months and solar years required careful observation over many years. The moon presented other mysteries too. Most of the time it moved smoothly through the sky, but occasionally, dramatically, it would vanish. Lunar eclipses occur when the Earth passes between the sun and moon, casting its shadow across the lunar surface. To ancient observers who didn't understand what was happening, a lunar eclipse must have been terrifying. The moon, the brightest object in the night sky, turning dark red or disappearing entirely. But early astronomers noticed patterns. Eclipses didn't happen randomly. They occurred at specific times when the moon was full and in particular positions relative to the background stars. By keeping careful records, Babylonian astronomers discovered they could predict eclipses using the Saros cycle. The moon also presented a navigational puzzle. Unlike the sun, which follows a predictable path through the sky that shifts with the seasons but is otherwise regular, the moon's path is tilted relative to the sun's path. The angle at which the moon rises and sets changes in a complex cycle that takes 18.6 years to complete. Ancient astronomers didn't just notice this, they tracked it. Some stone circles in Britain show alignments to the moon's extreme rising and setting points, the limits of its wandering across the sky. Building monuments aligned to these extreme positions required observations spanning decades, knowledge passed down through generations. The wandering stars. If the moon was the night sky's most obvious variable, the planets were its most perplexing. 5 planets are visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. To ancient observers, they looked like stars, points of light scattered among the constellations. But unlike stars, they moved. Venus is the brightest, outshining everything else in the sky, except the sun and moon. It appears as the evening star in the west after sunset, or as the morning star in the east before dawn, but never far from the sun. For a long time, ancient astronomers thought these were 2 different objects, an evening star and a morning star. Eventually, they realized it was the same object, cycling between evening and morning appearances. Mars is distinctive for its reddish colour. The Greeks associated it with Ares, the god of war, and the Romans called it Mars after their own war god. It varies dramatically in brightness, sometimes rivaling the brightest stars, other times fading to relative insignificance. Jupiter is the largest and moves sedately through the constellations, taking about 12 years to complete a circuit through the zodiac. Saturn is the slowest, taking nearly 30 years to circle through the constellations. Mercury is the trickiest to observe, never straying far from the sun, visible only briefly in the twilight glow after sunset or before sunrise. But the real challenge was understanding how they moved. Unlike the sun and moon, which move steadily in one direction against the background stars, the planets do something strange. Most of the time, they move eastward. Through the constellations, the same direction the sun moves. But periodically, each planet stops, reverses direction, moves westward for a while, what astronomers call retrograde motion, then stops again and resumes its eastward movement. Why? What could cause this strange behavior? For thousands of years, this was one of astronomy's great puzzles. Various theories were proposed. Perhaps the planets moved in circles within circles, epicycles, small circular orbits whose centers themselves orbited the Earth. Perhaps they moved faster and slower at different points in their orbits. Perhaps there were invisible influences pushing and pulling them. Greek astronomers, particularly Ptolemy in the 2nd century CE, developed elaborate mathematical models to predict planetary positions. These models worked. They could predict where a planet would be on a given date with reasonable accuracy. But they were complex, requiring multiple circles within circles, adjustments and corrections. The truth, that the Earth itself is a planet, orbiting the Sun along with the other planets, and that retrograde motion is an optical illusion caused by the Earth overtaking outer planets in our respective orbits, would not be widely accepted until the 17th century. But that didn't stop ancient astronomers from making remarkably accurate predictions using their geocentric models. The Babylonians could predict planetary positions years in advance. Greek astronomers refined these predictions further. They didn't understand why the planets moved as they did, but they'd mapped the patterns with sufficient accuracy to make predictions. And for practical purposes, for navigation, for timekeeping, for astrology, that was enough. The Maya astronomers. While European and Middle Eastern astronomers were developing their understanding of the sky, on the other side of the world, in the jungles of Central America, another civilization was conducting its own sophisticated astronomical observations. The Maya developed one of the most complex and accurate calendar systems in the ancient world. Actually, they used multiple calendars simultaneously, each serving different purposes. The Tzolk'in was a 260-day sacred calendar, used for religious ceremonies and divination. Its origin is mysterious. 260 days doesn't correspond to any obvious astronomical cycle. The Harb was a 365-day solar calendar, divided into 18 months of 20 days each, plus 5 unlucky days at the end. This tracked the solar year. These two calendars meshed together in a 52-year cycle called the calendar round. It took 52 years for a given combination of Tzolk'in and Harb dates to repeat. But the Maya also tracked longer periods. They used a long count calendar that measured time from a mythical creation date, which corresponds to August 11th, 3114 BCE in our calendar. Mayan inscriptions record dates in the long count with precision, marking events to the exact day. How did they achieve this precision? Through careful, systematic observation. Mayan cities contained buildings specifically designed for astronomical observation. At Chichen Itza, the structure called El Caracol, the snail, for its spiral interior staircase, has windows aligned to significant astronomical events. One window aligns with the setting position of Venus at its southernmost extreme. Venus was particularly important to the Maya. They tracked its cycle meticulously, recording its appearances and disappearances, its transitions between evening star and morning star. The Dresden Codex, one of the few surviving Mayan books, contains detailed Venus tables covering hundreds of years. The Maya calculated that 5 Venus cycles, 584 days each, equals 8 solar years, 365 days each. Actually, both equal 2,920 days. This near-perfect synchronization allowed them to predict Venus's position far into the future. They also tracked Mars, Jupiter, and Mercury, though with less intensity than Venus. They predicted solar and lunar eclipses. They observed the Milky Way and incorporated it into their mythology and timekeeping. All of this was accomplished without telescopes, without mechanical clocks, without any of the instruments we associate with astronomy. Just careful observation, meticulous record-keeping, and mathematical calculation. The Greek Revolution. Around the 6th century BCE, in the Greek colonies on the coast of what is now Turkey, a new approach to astronomy began to emerge. Greek philosophers didn't just want to predict where celestial objects would be. They wanted to understand why they moved. They wanted to build models that explained the heavens, not just describe them. Pythagoras and his followers proposed that the Earth was a sphere, a radical idea, since most people assumed the Earth was flat. Their reasoning was partly mystical. The sphere was the perfect shape, but also observational. During lunar eclipses, the Earth's shadow on the moon is always round. The only shape that always casts a round shadow is a sphere. They also noticed that as you travel north or south, different stars become visible or disappear below the horizon. The pole star sits higher in the sky the farther north you go. These observations make sense if the Earth is a sphere, less sense if it's flat. Eratosthenes, in the 3rd century BCE, went further. He'd heard that in Siene, modern Aswan in Egypt, the sun shone directly down a deep well at noon on the summer solstice, meaning the sun was directly overhead. But in Alexandria, 800 kilometers to the north, the sun was never directly overhead. On the summer solstice, Eratosthenes measured the angle of the sun's shadow in Alexandria at noon. He found it was about 7.2 degrees from vertical, about 1/50th of a full circle. If the Earth is curved, he reasoned, and the sun's rays are parallel, which they are to a very good approximation, given the sun's immense distance, then this 7.2 degree difference in the sun's angle must correspond to the curvature of the Earth over the 800 kilometers between Alexandria and Siene. Simple geometry. If 800 kilometers equals 1/50th of the Earth's circumference, then the full circumference must be about 40,000 kilometers. This is astonishingly close to the actual value, about 40,075 kilometers at the equator. Using nothing but a stick to measure shadows, some basic geometry, and the distance between two cities, Eratosthenes calculated the size of the Earth with remarkable accuracy. Greek astronomers also measured the distance to the moon. Aristarchus, in the 3rd century BCE, used observations of lunar eclipses to estimate that the moon's diameter was about 1/3 the Earth's diameter. The actual ratio is about 0.27, quite close. By observing how long it took the moon to pass through the Earth's shadow during an eclipse, and knowing the moon's approximate speed in its orbit, he could estimate the moon's distance. His calculations placed the moon about 60 Earth radii away, again, remarkably close to the actual average distance of about 60.3 Earth radii. These weren't wild guesses. They were careful calculations based on observations and geometry. The cosmic blueprint. Perhaps the most remarkable aspect of ancient astronomy is this. Without understanding the true structure of the solar system, without knowing that the Earth orbits the Sun, without telescopes or photography or any modern instruments, ancient astronomers achieved extraordinary accuracy. The Babylonians could predict planetary positions and eclipses. The Maya calculated the Venus cycle to within hours over centuries. The Greeks measured the size of the Earth and the distance to the Moon. They did this through patience, through systematic observation over long periods, through mathematical modelling, and through the accumulation of knowledge across generations. Each civilization, built on its own observations, developed its own techniques, created its own explanatory frameworks. Some of these frameworks were more accurate than others. The Greek model of the solar system, with its epicycles and deferents, was complex and cumbersome compared to the later heliocentric model, but it worked well enough for predictions. The key insight shared by all these astronomical traditions was this: the sky isn't chaotic. It follows patterns. Those patterns can be discovered through careful observation. Once discovered, they can be used to make predictions. And those predictions can be tested against reality. This is science at its most fundamental. Observe, find patterns, make predictions, test them. The legacy. Stand outside on a clear night, far from city lights, and look up. The sky you see is fundamentally the same sky our ancestors saw thousands of years ago. The same stars, in the same patterns, wheeling overhead in the same endless dance. What's different is our understanding. We know now that those fixed stars aren't fixed at all. They're moving through space at tremendous speeds, but they're so far away that their motions aren't visible over human timescales. We know that some of those stars are actually entire galaxies, each containing hundreds of billions of stars. We know the moon doesn't generate its own light, but reflects the sun's. We know the planets are worlds in their own right. Mars, with its polar ice caps and ancient river valleys. Jupiter, with its swirling storms and dozens of moons. Saturn, with its magnificent rings. We know that retrograde motion is an optical illusion, that the Earth orbits the Sun, that our Sun is one of hundreds of billions of stars in our galaxy, and that our galaxy is one of hundreds of billions of galaxies in the observable universe. But all of this modern knowledge rests on a foundation laid thousands of years ago by astronomers who had none of our instruments, none of our technology, none of our accumulated knowledge. They had only the sky, their eyes, their minds, and their patience. And, with those tools, they began to decode the cosmos. They discovered that the universe operates according to rules, that those rules can be discovered, that nature is comprehensible to human reason. This may be their greatest legacy. Not any specific measurement or calculation, but the fundamental conviction that we can understand the universe, that it's worth trying, that patient observation and careful reasoning can reveal nature's secrets. Every time a modern astronomer points a telescope at the sky, every time a spacecraft flies to another planet, every time we make a new discovery about the cosmos, we're continuing work begun thousands of years ago by those first watchers of the heavens. The night sky still wheels overhead, just as it did when our earliest ancestors first looked up and wandered. The stars still trace their eternal paths. The moon still waxes and wanes. The planets still wander among the constellations. But we see it differently now, not because the sky has changed, but because we've learned to see more deeply, to understand more fully, to ask better questions. The ancient astronomers gave us more than just calendars and eclipse predictions. They gave us a way of thinking about the universe, systematic, mathematical, predictive. They showed us that the chaos we perceive can conceal deep order, that patterns can be found if we look carefully enough, that the universe reveals its secrets to those patient enough to observe and clever enough to interpret. On clear nights, in dark places, the Milky Way still arcs across the sky, a river of stars, a glowing band of light that ancient peoples saw as a road to the heavens, a trail of spilled milk, the backbone of the night. We know now that it's our home galaxy seen edge on, hundreds of billions of stars spread across hundreds of thousands of light years of space. But whether we see it as mythology or science, as symbol or reality, its beauty remains the same. And the impulse that drove our ancestors to watch it, to study it, to try to understand it, that impulse remains the same too. The sky calls to us still. The same questions that fascinated ancient astronomers still fascinate us today. We've answered many of them, but each answer reveals new mysteries, new questions, new frontiers of understanding. The work begun thousands of years ago continues. The great conversation between humanity and the cosmos started when the first curious mind looked up at the stars and wondered what they were, goes on. And on clear nights, when the stars come out and the ancient patterns appear once more in the darkness, we're connected to all those who came before us, the Babylonian scribes with their clay tablets, the Maya astronomers with their stone observatories, the Greek philosophers with their geometric calculations, the builders of Stonehenge with their massive stones aligned to the solstice sun. We're all watchers of the same sky, all trying to understand the same cosmos, all part of the same ancient quest to decode the heavens. The stars shine down, as they always have, and we watch, as we always have. And slowly, patiently, generation by generation, we learn. The story continues. The night sky still has secrets to reveal, and somewhere, someone is looking up, asking questions, making observations, adding to the great accumulation of human knowledge that began when the first astronomer counted the nights between new moons and wondered why.